Now, if we wish to find the transmission and reflection coefficient for magnetic wave, then in case of magnetic wave, the reflection coefficient will be reflection divided by incidence. The formula will remain same. However, the direction of H is opposite to E, so it is placed here, and the ratio of these two will be same as it was in the case of electric field. So it will be minus times minus 2 minus eta 2 minus eta 1 divided by eta 2 plus eta 1, as we have done here. So after simplification it will give eta 2 divided by eta 1 plus eta 2. So this is the reflection coefficient for magnetic field. Similarly, the transmission coefficient can be written as, the transmission remains in the same direction, h t naught. So on the basis of that, it will be 2, the medium is 2 eta 2 divided by eta 1 plus eta 2. Okay. Now these two are the final equations that we have regarding the magnetic field component of a electromagnetic wave to find the reflection and transmission coefficient. So in this way we have 4 final equations to have the reflection and transmission coefficient for electric and magnetic field component of the electromagnetic wave, when we have assumed the electric field direction remains. Next, we can consider the case when the direction of magnetic field does not change. As we have done in case of electric field, the study we have done until now. Now we will consider for magnetic field the direction does not change, and for this case I'm not writing the I'm not deriving, just I'm writing the final result. That is, the reflection coefficient will be if eta 1 minus eta 2 divided by eta 1 plus eta 2, that is simply the reflection component divided by incident component. Okay. Now the transmission coefficient will be transmission component divided by incident component. So this is eta 2, and the electric field in this case will be a reflection component when it is assumed that the magnetic field component direction does not change. It will be minus a reflection, because direction will change in the case of electric field. Then to make the propagation the direction proper, it will be equal to the, I am writing just final findings, you can verify this by your own, and the transmission coefficient will be E T naught E I naught, that will give you 2 eta 2 divided by eta 1 plus eta 2. In this way, these 4 equations are final equations for this case. Okay, hope these all points are okay to all of you. Now you can verify this. Now let us start new topic, that is transmission line. Our discussion in last topic was on wave propagation in unbounded media. Such wave propagation is said to be unguided, and we found that in unguided propagation the plane wave exists throughout all space and the electromagnetic energy associated with the wave spreads over a wide area, and that is used in radio or TV broadcasting or some many more applications. Where the information is being transmitted is meant for everyone who may be interested in that. And another mean of transmitting power or information is by guided medium, or we can say that by guided structure. In it, the propagation of energy takes place from the source to the load, and we have typical example of such structures as transmission line and waveguides. So transmission lines are considered in this discussion, and we know transmission lines are commonly used in power distribution at low frequencies. We have studied this in different courses, and in communication at high frequencies. A transmission line basically consists of two or more parallel conductors used to connect a source to a load. And the transmission line problems usually solved by electromagnetic field theory and electric circuit theory, the two major theories on which electrical engineering is based. In this discussion, we use circuit theory because it is easier to deal with mathematically. The previous concepts that we have studied regarding wave propagation, such as propagation constant, reflection coefficient, and some more covered in the previous discussion, we will apply here. And our analysis of transmission lines will include the derivation of the transmission line equations and characteristic quantities. Now let us start the detailed discussion on the transmission line. So we will start from the equivalent circuit of transmission line. Now let us do the detailed discussion on the transmission line, where we can have two conductors placed parallelly as shown here, and if source is connected to the transmission line, the voltage and current wave traveled from source to the load along the wire. Now if we will try to find the equivalent circuit of the transmission line, then we can find that has resistance, inductance, conductance and capacitance. These are the primary parameters of the transmission line. These are also known as primary constants of the transmission line. So we can write it down: primary constants of transmission line, that is resistance, inductance, conductance and capacitance, and the parameters that are derived from these are known as secondary constants or secondary parameters of the transmission line. Now few points are here to required to remember here, that is these parameters are in per unit length. So the unit of this will be ohm per meter, Henry per meter, mho per meter, farad per meter. Okay. Now for discussion purpose, let us assume that the source is placed at just, we will come at that point. Let us redraw it. Now for the discussion purpose, let us assume that the voltage and current waves are traveling in z direction. So let us consider that the source is placed as z is equal to 0, Now the waves are traveling in z direction from z is equal to 0 onward. Here the position will be z plus delta z. So we are considering the transmission line for delta z length. So for delta z length, the resistance will be as it is per unit length. So for delta z, the resistance will be R delta z, L delta z, G delta z and C delta z. Now let us try to find the voltage and current wave equations from this equivalent circuit. So if we will apply KVL by applying the voltage source, and if we apply voltage source, then the current that is flowing here will be I source Z. The voltage that is obtained at the receiving end or at the load side, we can say it is Z plus delta Z, and the current that is flowing from here, part of it is diverted to the conductance and the capacitance through it, and the part of it will flow through there. So the current that is flowing here, we can say Is Z plus delta Z. We can assume like that. Now apply the KVL in outer loop to derive the voltage and current wave equations. So for voltage wave equations, let us apply the KVL at the outer loop. So we can have Vs Z if we are considering from minus to plus positive, then from positive to negative it is considered as minus. So it will be minus Is Z R delta Z, voltage drop across that, and voltage drop across j omega L, where this is the frequency for this length, and it is the impedance multiplied with the current will give us the drop across that and the outer one. So that will be Vs Z plus delta Z. According to the closed circuit, sum will be 0. Now let us simplify by having the this term in another side and current terms in another side. So for that we can write Vs Z minus Vs Z plus delta Z is equal to, see, delta Z and delta Z are common in these two. If you will bring it another side, then delta Z we can bring here, and the remaining term will be Is Z R plus j omega L Is Z. We can write like this. Here we find Is Z is common, so we can write Vs Z minus Vs Z plus delta Z divided by delta Z will be equal to the R plus j omega L multiplied with Is Z. Okay. Now if we consider that the delta Z is very small, or that we can write like this, limit delta Z tends to 0. If we apply this limit, then what we can find here, Vs Z minus Vs Z plus delta Z, this will be the differential voltage, we can write like this, and it can be differential length will be equal to, there is no delta z, so there will be no change. It will remain as it is. Now let us differentiate once again to get the wave equation similarity. So we can write divided by E square will be equal to the R plus j omega L, this is z dependent, so it will be d I s z over dt dz. This is the final equation that we can have for future reference. So equation number 1, equation number 2. Similarly, apply the some rule to find the current waves. So for that purpose, we can consider the we can do node analysis at this point. So the sum of the currents at this will be equal to the 0. So we can write the node analysis at point P. We can say IS. Okay, we can consider any assumption that the incoming current can be considered as negative and leaving current can be considered as positive. So from there we can write ISZ with minus sign, and the leaving current is ISZ plus delta Z here, and the current that is flowing here, we can consider the voltage across this multiplied with this conductance. So the current is again leaving, so it will be positive here. The conductance will be G delta Z plus C delta Z. Okay, so here we can write G delta Z plus J omega C delta Z. Conductance for voltage Vz plus delta Z. The sum of the current will be equal to the 0 at any particular node. Now if we will simplify similar to that, following the same way, then we can find, I'm not going to solve, just I'm writing the final equations that we have find it out in the case of voltage. We can write d I s z divided by dz will be equal to the G plus j omega c times V S Z. This is only when delta z tends to 0. When delta z tends to 0, then it will be VSZ. Now if we will do the double derivative, yes, we will take the derivative once again, then we will find d square ISZ divided by z square will be equal to the G plus j omega c. VSZ can be written as dVSZ divided by dz. Now this can be considered as equation 3 and this can be considered as equation 4. Now we have these 4 equations for further discussion. Now let us try to relate these final equations from wave equation. So if we will put the value of DIS from DIS by dz here, then we will find d square VSZ z square is equal to R plus j omega L. It will be G plus j omega c times VSZ. I am putting the value of this here. Then we are finding the voltage wave equation. Similarly, we can find the current wave equation. Why I am saying the voltage and current wave equation, we will see it here. G plus j omega c multiplied with the value of this from here. So R plus j omega L times IS Z. Now these two are the final form of the equations that we have. If we will bring it minus equal to 0, similarly we can bring it here, that will be minus equal to 0. We can do like that. Relate from wave equation that we can have del V square Vz del Z square minus gamma square. This is the form of wave equation. Now relate this with this, we find that this is nothing but admittance, this is impedance. Similarly, we can write in the case of current as well. And now if we will try to find the solution of these differential equations, then we can have Vs Z is equal to the positive traveling wave gamma Z, the positive Z direction, and the negative traveling wave that is considered as positive gamma Z. Negative and positive is just in the direction of the propagation. And similarly we can write for current as well, that is Z will be equal to the positive traveling, positive from here, positive traveling current wave and plus negative traveling current wave. These are the solutions of this and the another form of the wave equation that we can get from here. So these components are known as forward traveling wave and these are backward, or we can say reverse traveling wave. Okay. Now from here we can find gamma is equal to the, if it is considered as impedance, it is considered as admittance Y, then we can say gamma is equal to Z times Y. And in the wave equation we have studied gamma is equal to attenuation constant plus phase constant. So if we will solve this, then we will find the alpha and phase constant in the case of transmission line as well. In the case of the unguided wave propagation, we have discussed the intrinsic impedance. Here in the case of transmission line, we will discuss the characteristics impedance. And it can be defined as the ratio of the forward traveling voltage wave to the forward traveling current wave. So from here we can write it is the ratio of the forward traveling voltage wave divided by the forward traveling current wave. And it can be also written here the ratio of the reverse traveling voltage wave, the reverse traveling current wave, but it is traveling in reverse direction, so it should be minus here. And it can be further written R plus j omega L divided by, related to current, that is G plus j omega c. So these are in characteristics impedance in terms of primary constants. Now consider the different cases of a transmission line, different cases of the guided wave propagation, to find the different parameters of the line. So let us start the lossless transmission line. Lossless transmission line. And in case of lossless, what it means, the losses that are occurring, that is R and G, they are 0. So lossless means the resistance and conductance of the line is 0. And if these are 0, then try to find the different parameters that we have studied in case of unbounded wave propagation, or we can say unguided wave propagation. That was the alpha, beta, gamma, velocity, I think intrinsic impedance. Here it is characteristic impedance. So we will try these parameters here once again for lossless transmission line. So let us start from finding alpha and beta. So we know gamma is equal to alpha plus j beta. That can be written here as R plus j omega L. In the few minutes before, we have seen that it is R plus j omega L times G plus j omega C zy. That is nothing but gamma, that is alpha plus j beta. For lossless transmission line, these two terms will be equal to the 0, and the remaining term will be j square. J will be outside, omega square, omega will be outside, j omega will be outside, under root LC. These are alpha plus j beta, and it can be further written as 0 plus j omega under root LC. Now try to find alpha and beta from here. We can say alpha is 0 and beta is omega under root LC. In the case of wave propagation, plane wave propagation, that we have studied in previous chapters, there it was omega under root mu epsilon. Mu is related to inductance, epsilon is related to capacitance. So here for lossless transmission line, the attenuation constant is 0, that is alpha, and the phase constant is omega under root LC. Now let us try to find the intrinsic equivalent, that is characteristics impedance of the transmission line. So in terms of primary constant, we have it is equal to the R plus j omega L divided by G plus j omega C. For lossless, these two parameters are 0. These two will be cancelled out. The remaining term will be under root L by C. So this is the alpha, beta and characteristics impedance of the transmission line. Now the velocity, phase velocity, we can say that was omega by beta. We have discussed this formula already. So omega divided by omega under root LC. Phase constant we have derived from here, so it can be written as LC. So in this way we have alpha, beta, gamma, phase velocity and characteristics impedance for transmission line.